Hello, this is Dr. Lori. Welcome to this discussion on estimation of population proportion. We have already spent quite a bit of time talking about estimating population means, and just as a quick review, when we're thinking about continuous variables and estimating that would be estimating a mean about a continuous variable. When we are looking at any kind of categorical variables, we have proportions instead of means, and so this would be for categorical variables. And in this specific case, I'm going to be showing you about a categorical variable that has two categories. And so here's our proportion, and we're going to have two categories. Now, if you remember, we start off in any time that we're looking at data, we start off with some kind of a population that we're trying to either describe or measure or that kind of thing. And because it's unwieldy to collect information on every single person in the population, we take a sample instead. And we want to do this in some way that is representative. So I'll put rep here. So it represents, this sample represents the population. Often that's going to be a simple random sample. And once we have our sample, these are all the people that we have in our study group, then for each person we measure something about those people. So for each person we may measure whether they're a smoker or a non-smoker, we may measure their height and weight, we may measure male-female, and that sort of thing. In this particular case, we're going to measure whether they're a smoker or a non-smoker. Now, we get a sample of 57 people, and we ask all of them if they're smoker or non-smoker, and 17 of them say that they're smokers, and 40 of them say that they're non-smokers, for our total of 57. So here's our total. 57 is the same. Now, what we're measuring is what proportion of our sample are smokers. And we use a measurement called p-hat. And just as kind of like a reference, we're going to be looking at what the location is for that particular proportion. So p-hat is the proportion that is measured in our sample, and that is x, or the number of positives, whatever it is that we're measuring, divided by n, which is the total number that whole group comes from. By default then, this group of non-smokers is n minus x. So the two here need to add up to the total amount. Sorry, that's my puppy barking at somebody who's walking by. So in this case, p-hat is x over n, which is equal to 17 over 57, and we call this an unbiased estimate because if we have indeed sampled a representative sample and we've measured accurately, that's supposed to be an A, don't know why it went all the way up to the top. If we've taken our measurement accurately, then this is an unbiased estimate of what we would find in the population if we were to be able to ask every single person. So an unbiased estimate of the population proportion. So here we have the sample measurement is p-hat. We're going to then infer something with hypothesis testing about the population proportion p. Now this gets confusing because we also know of another p that's called a p-value. So when I refer to p-value, I will always say p-value. And when I'm talking about this population proportion, I'll represent it as a lowercase p. So that's a lowercase p. This is a lowercase p-hat right here. So what we measure in our sample is an unbiased estimate of what we would find in the population if we were to ask every single person. And the reason that it may not be exactly the same as the population proportion is because of that random error. So in terms of the location here, what we end up with is p-hat for being a smoker is equal to 17 over 57, which is equal to 0.3. 0.298, and that's rounded. So in terms of location, we have 29.8% of our sample were smokers when we asked them that question. So one of the things that I would like to sort of point out is that this proportion that we end up measuring ends up being something a bit of an average. Like in terms of when we're calculating mean, we're calculating the average of all the measurements. Well, what ends up happening is smoker, let's say, is coded as a 1. That's the X that we're interested in measuring. Non-smoker is coded as a 0. So what we end up with, let me move over here just a little bit. What we end up with is 17 times 1, which is equal to 17. We end up with 40 times 0, which is equal to 0, divided by the total of 57. And so if we were to enter all of those ones and zeros into some kind of a database and calculate the average, we would come up with this very same number, 0.298. So it is actually an average of sorts, and for that reason, we can treat it as an average when we're doing a kind of a hypothesis test. So let's go ahead and take a look at the hypothesis test. Now that we have our point estimate, now we want to test some kind of value, whether what we found is equal to that particular value. And before we do the actual hypothesis test, I want to take a look at a little bit of the numeric reasoning behind it, and that is that we are able to use something similar to what we used when we were sampling means, even though we're testing something that has this binomial quality. In other words, our question is, are you a smoker or not a smoker? It's not a continuous variable, but because it has it's this type of average, then we can treat it that way when we're doing some kind of hypothesis test. Now, the criteria for whether we can use the normal approximation to the binomial is that our n times p times q must be at least equal to 5. And in this case, we're looking at a null hypothesis where we want to know if the population proportion is equal to some null value, and I'll call that P0. And specifically, let's just say that we want to test whether our population has the same average as other locations in the United States. Our particular average was 29.8%, and the average in the US is 21%. So let's go ahead and add that to our hypothesis. In other words, we want to know if the population proportion is equal to 21%. So I'll just write that on here, equal to 0.21. So that's what we're testing. The alternate hypothesis is that the proportion is not equal to 0.21. Could either be higher or lower, and that allows us the most reliability of our findings. So we need to know first if it's even valid for us to perform this test. So we're going to put in some of the numbers. Let's say we have our sample of 57. We multiply that times 0.21, 0.21, and if you remember, Q is just the inverse of P. Those two added up together need to equal 1, and so by default this is 0.79. So if you multiply those three numbers by each other, you actually come up with 9.5, and that is in fact greater than or equal to 5, so we can use this normal approximation to the binomial. We have a large enough sample size that we are able to use this particular distribution as the basis of our hypothesis test. Now you can imagine that if this number 57 got smaller and smaller and smaller and smaller, then this number also would get smaller and smaller, and at some point it would be less than 5. And so it's not automatic that we get to use the normal approximation to the binomial. We have to meet this criteria in order to be able to use this test. So here we have the setup of our hypothesis test, and I want to give you a little bit of background, and this should be somewhat familiar compared to what we did with means. And I call this exercise, we never do this, because we only test one sample. But let's just imagine here we have our population. We have our whole group of, all the little people who live in whatever town. So this is our hundreds or thousands or tens of thousands of people. And we draw a sample. I'm going to call it a simple random sample, a size of n. And the population itself does have a proportion. But this simple random sample may or may not have that same proportion. It may be a little bit higher or lower. So let's say here's the proportion. This particular sample, size of n, is going to have a p-hat. It's going to have a proportion that's equal to the number of x's, number of smokers in that particular sample divided by n. And so let's say that proportion is slightly lower than the actual population proportion. Here's our population proportion, lowercase p. Let's just imagine then that we take another sample, and it's a simple random sample, size n. This one, just by randomly selecting 57 people, we might get a different proportion, and that's going to be equal to the number in that sample who are smokers divided by the n. And just out of demonstration, let's go ahead and put that here. So here's p-hat 2, here's p-hat 1. If we repeat this over and over and over, we draw all these different samples, we would end up with different proportions depending on how many in that particular sample ended up being smokers. And we would have a range. And so we end up being able to see this as this normal distribution. And that's what this normal approximation to the binomial is it is a distribution of these hypothetical p-hats. If we were to sample over and over and over and over and over from the same population, we would get a variety of different sample proportions. And our question then is whether it's reasonable we extrapolate then that to our actual hypothesis. So let me back up just for a second. The other thing to remember is that this distribution has a mean, and if this is a normal approximation to this binomial, then the distribution of z-values, oops, let's undo that. Don't need that line. The distribution of z-values will be similar to what we're used to. A z of 0 is in the middle, and then 1, and then plus 2, and minus 1, and minus 2, just like what we saw before. And so we end up with, because we have a large enough sample size, we can use this to approximate what our distribution will look like and whether this will be related to our null and alternate hypothesis. Okay, so that's where this distribution comes from. And I'm going to go ahead and move down then. When we're actually testing this, then we need to know a couple of different things. First of all, we need to know what our test proportion is, and that's going to be equal to 0.21. We also need to know the standard error, and it just so happens that standard error is equal to the square root of p times q over n. And so in this particular case, we have 0.21 times 0.79 divided by 57, and we calculate that and then take the square root of it, and we end up with 0.054, and I'll just put dot 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 because that includes some rounding. And so if we know what we're testing in terms of a location, and then we also have a measure, some kind of measure of spread, then we can calculate a z-value that goes with this based on that normal approximation to the binomial that's very similar to what we've seen before. Basically, we take our population proportion, or our sample proportion, which is p hat, we subtract out the test value, 0.21, and then divide that by the standard error, which is this right here. So let's go ahead and plug those numbers in for this example just so that you can see where those go. Remember how we got 29.8% of the population or of the sample was smokers? So we have our 0.298, and then we're going to subtract what our null hypothesis is, or 0.21, and then divide that by our standard error, which is 0.054, whatever, dot dot dot. Now it's important sometimes to hang on to those decimals. I would say that if at all possible, try not to round too early in the calculation process. But what you end up here is, if you calculate this out, you end up with 1.63. So a z-value of 1.63. Now, if you can remember, kind of go back to what you know about this normal distribution, if we were to calculate some kind of a 95% confidence interval, this plus and minus 2, this is 95%, 1.63 is somewhere in here, right? It's between 1 and 2. So it's kind of in what we would consider to be, well, that's possible. That's not so far outside of what could be expected. So if we go back to our hypothesis testing, we started off by saying we want to test whether the real population proportion is equal to 21%. And we ended up with a z-value of 1.83. Our next step is to convert that z-value into a p-value. You can do that by looking at tables or running this in a statistical software. Basically, for every z statistic, there is a corresponding p-value. And in this case, the p-value is 0.1031 for a two-tailed test, 1031. Now, if before we ran the test, we decided our alpha was going to be 0.05, this number is not less than 0.05. 0.1 is greater than 0.05, which goes along with our observation that what we see is that 1.63 is kind of within this 95% confidence area. It's not outside, it's not out here in the tail. And so the z-value and the p-value really tell you much the same thing, in that the z-value is less than about 2, the p-value is greater than 0.05, and so you would come to the same conclusion based on both of those numbers. So that is a summary of looking at the actual location. And so here we have our location value. We calculate it as 29.8, and that is not, it's different from 21%, but it is not statistically significantly different from 21%, which was what our test hypothesis was. The second thing that I would like to do is talk about spread, and specifically confidence interval. And so this is just another way of looking at the same exact kind of question. So let's go ahead and go down here, and there is a special method for hand calculating a 95% confidence interval. It's called the +4 method. And basically what we do is we're going to take this, our previous calculation, and we're going to do something called +4. So instead of having p hat, we have this p with the squiggly line over it. Instead of having Q hat, we have a Q then with a wiggly line. And instead of having N of our sample, now we have an N with a squiggly line by adding 4 to whatever it is that we're doing. And specifically, the +4 method has you add 2 to the top number and 4 to the bottom number. So let's plug our 17 and 57 in here. What we end up with then is we end up with 19 over 61. And so this gives us a correction that corrects for the fact that just looking at the regular proportion here, the 17 over 57 by itself, is usually somewhat off. And so this corrects for that inaccuracy. And as you can imagine, the larger the sample size is, if this was 100 or 1,000 or 10,000, adding 2 and adding 4 does not make all that much of a difference to the overall ratio between the two, but as the number gets smaller and smaller and smaller, then this makes more of a correction. So it's more important for smaller sample sizes and less important as the sample gets bigger and bigger and bigger. So here we have our 19 over 61, and so our new P or proportion is equal to 0.3115, and Q is just the inverse of that. The two numbers need to add to 1, so 1 minus 0.3115 is equal to 0.6885. So those two numbers should add up to 1. And so my new standard error is going to be equal to 0.3115 times 0.6885 divided by my new n, which is 61, and take the square root of that whole thing, and I end up with a standard error of 0.0593. That's not good. Let's go ahead and draw that again. 0.0593. That's better. Somehow my pen was skipping. Now, if you compare this adjusted standard error to the standard error that we calculated before, let's actually go over here, 0.54. So here's our previous one. You'll notice that it's slightly larger, and that's the effect that adding 2 to the top and 4 to the bottom will have on that p-hat value. It'll bring it closer to 0.5. It'll bring it closer to the middle. So now we have our new standard error. And you remember about calculating confidence intervals. Basically, what we need to do in order to calculate this 95% confidence interval is we have a new, let's go ahead and draw it down here. We have a new curve with a middle point of 0.3115. We need to go 1.96 z-values to the right and 1.96 z-values to the left in order to get the 95% confidence interval. Remember, plus and minus 1.96, which is approximately 2, is equal to that z-value of the top and bottom. So if we take 0.3115 plus the 1.96 times this value, 0.0593, we do the same thing on the bottom, 0.3115 minus 1.96 times 0.0593, and what we end up with is 0.1953 and 0.4277 as our kind of bounds. In other words, here we have our 95% confidence interval. And so now what we've done is we've created a confidence interval, and I'm just going to round it here, of 19.5% all the way up to 42.8%. is a 95% confidence interval around what we think the proportion is for smokers. And so let's go ahead and go back up to the top and put that in. So here we have our 95% confidence interval, and that is 19.5%. So anywhere between 19.5% and 42.8%. We calculated a point estimate here, and this gives us a range of values based on this normal approximation of the binomial and the +4 test that would theoretically capture 95% of these simple random samples. So if we were to sample over and over and over and over again and have all of these different proportions that are possible, then 95% of the time that interval would include our particular p-hat for the simple random sample that we have measured. So I hope that gives you a good idea about estimating for a population proportion. This is probably something that is used less often, but conceptually is important as a foundation for what we're going to be doing starting next quarter. So I hope you have enjoyed this lesson, and I look forward to seeing some of your work in class.